because I'm going in the negative direction here. Displacement's negative 300 meters. Because I'm not turning around, that would also be the distance, because distance is just, you know, how far I've actually traveled, but I'm only going in one direction here, so that would be the distance.
So,
My distance would be 300, positive
so
300.
it'd be positive 300.
Yeah,
Okay, well, that's the problem that was on one of your old tests. But then we had a problem on, Master Set 3, where it said it went from 0 to 80. And then in 8 seconds. You would do the same thing?
yeah,
Okay. Cause it's not ending in 0, but we're starting out at 0?
yep.
Okay.
As
so
long as the sign doesn't change,
same
you're just
thing.
traveling in one direction,
Okay.
and you can play a little fast and loose with some of the language.
Alright, awesome. And then I need help with the acceleration on Earth and on Moon. On the Moon.
As in,
So like this one, it says, in this experiment, I push on my 80 kilogram partner who is sitting on a frictionless level floor of course with 200 newtons of force parallel to the floor. So the weight, to find out the weight, you do W equals mg.
yep,
Okay, and then the mass is the same on Earth and the Moon.
yes.
Now I'm confused with the acceleration. It says, what is his acceleration on Earth?
All right, in that particular example, that was master set,
No, that was
I think there was a,
the fall test, but we did have one on the master set, you
Okay.
are right.
so I'm pushing on a person here on a frictionless floor.
Mhm.
So I'm pushing on him. There are 3 forces acting on the object in question. You have his weight acting down. There's normal force acting up, and then there's this push coming from me. I'll just label it cleverly F for force. I apply this force to him. These two are gonna cancel each other out. They're gonna neutralize each other because he's moving horizontally, these two are vertical. And so the total force, because if I plug in a Newton's second law, F equals ma, that force is the total force. Well, if they cancel each other out, that's all I'm left with.
It would be the 200.
Yeah.
Okay, so you do 200 divided by his mass, which is 80.
Right,
And would that be the same on Earth and on Moon?
right, because on Earth, we still deal with a frictional situation. It's a different weight, it's a different normal force, but they still cancel each other out.
Okay,
So on Earth, you still get the same answer.
so the weight is the only thing that changes? Cause you would do, you
The-
have W equals mg, so then you would do his mass, which is 80, times 9.8 for Earth. And then the Moon, it would be 80 times what, 1.6?
Something like that.
Is that right?
Yes, that is right. And I will add one thing, the weight does change, absolutely, just as you laid out. The normal force as a consequence would also change.
Okay, yeah, that makes
Because it
sense.
requires more force to hold them up now.
Okay, alright, thank you.
Yep. All right. Jasmine, you were about to ask a question, I think a moment ago.
I think it's Master Set 3, question 4 with the 2 balls. I was wondering, is it 100 meters? Cause I got it wrong, but I can't remember.
Yeah, it is, and it says it's the ball A never catches up to ball B. But it's also 100 meters because that's when,
They would catch up together because that's when they hit the ground.
yeah.
Yeah, so I accept either they don't catch up or at 100 meters. If I misgraded it, then just bring it back up to me. But yeah, there were 2 answers there that I accepted. My original intent was it doesn't catch up, but then when people said they catch up on the ground, I thought, oh, well, I guess that's true too. Okay. And then there are a couple other hands. Emily?
So, 11 on the, fall 2012, test, the letter C, I was confused at how that was calculated because there was some missing information. And I tried working it backwards, but I couldn't figure it out.
So it starts at rest, you have acceleration and time. So for an object starting at rest, the displacement is 1/2, so starts at rest. Displacement is 1/2 AT squared. This is just a slightly more generalized version of Hewitt's, I drop an object, how far does it fall in a certain amount of time? And he says it's 1/2 gt squared, because the acceleration is little g. But in that particular case, I think it's 1/2 times 5 times 3 squared.
What question is that?
From the fall 2012, you said?
Yes.
What question?
It's
11.
11, letter C.
Thank you.
And so, 22.5 meters.
And that's the what?
That is for this object, based upon part B, the acceleration was 5 meters per second squared. That was the answer to part B. Part C said, if it starts at rest, how far does it go after 3 seconds? And so the time was 3 seconds. It started at rest, so it could use this equation. This is the answer to whatever part B was. If you had a different value for part B, then I would expect a different number in there for your part C. Which does bring up, let's suppose that you know how to do part C, but can't figure out how to do part B, and you need part B, just make up a number for part B and use that for part C.
We get half credit for that?
You would get, if you make up a number for part B and use that number for part C, you could potentially get full credit for part C and just lose points on part B.
Oh, that's nice.
When you make up a number, please don't make the acceleration 0. Don't choose 0.
So like, that would be used if they say a ball is dropped off a building, and how far did it travel after it dropped?
Same equation.
And then also like how long it took the fall?
So how long, if you know how far it goes,
Yes,
then you know that number, and hopefully you know that number,
yes,
and now you're solving for a different unknown.
okay,
But same equation, assuming it's dropped.
alright.
So it's the same equation as the movie, free fall from rest equation,
Yes.
essentially, but instead of the force of gravity, you use whatever acceleration you have.
Yes. And Jessmira, I saw a hand back there, it's either Haley or
Yeah.
Jessmira.
I know you talked about this problem, but I forgot. Master set 2, number 13, 35 kg boy on a 6 kg sled. I had trouble with 6, D, and E. I mean, C, D, and E.
All right, so, how many, in terms of timing, how many more questions do you think we've got here? Or can we make Jessmira's the last, or is that,
That's fine.
Oh,
Sorry.
I have one question, just like not really with this, but I'm saying like for the following week, do you know like what the time frame would be? Like,
yeah, no.
okay,
You know, when Mike came in here, I was asking about test corrections, and yes, there were test corrections. He said, was asking when they would be due, and he said, is it due in half the amount of time as it usually is, because of the shortened semester, because it's a 7.5 week course. My mind still does not go there. I still do not think, oh, gosh, this ends in early March. So, we'll get wherever we get. Yeah, if I do it, by Thursday, I'll hopefully have that. And if I don't, harass me.
okay.
All right, Jessmira. So in that trouble right there, we had boy on sled, and the sled was moving at a constant velocity horizontally. I think I said constant speed horizontally, implying that the direction was constant, speed was constant, therefore velocity is constant. If velocity is constant, that means my change in velocity is 0. That's what, if change is 0, it's something that's constant. Which means that my acceleration is 0, which means that the net force is 0. If velocity is constant, we're in equilibrium. If we're in equilibrium, all these are true. So if it's meters per second, that's meters per second squared, and that's meters.
Net force is the same thing as total force, right?
Yes, yes. So, if we look at the forces acting, so we've got sled, we have boy, or kid, or whatever I labeled them. So the sled is being pulled with, I gave a value for that of
42 newtons.
Yeah.
42 newtons. There is friction acting here, so there's got to, since it's in equilibrium, it's got to be 42 newtons acting back. If this were not 42 newtons acting back the other direction, then it would not be in equilibrium. The boy has some weight, so W sub B. The ground down here, W sub B. There's a normal force acting on the boy, and that's pushing down on the sled. The sled has weight. And there's a normal force pushing up on the sled and down on the ground. And then there's a reaction to the friction force. Since the boy is in equilibrium, the letters that you mentioned that you were having difficulty with were some of the later ones.
It's a magnitude of normal force acting on the sled from boy, let's see, 6
Alright.
kg, 35.
The magnitude of total force acting on the sled, and then the CP and E. So normal force on sled from boy, and normal force on sled from ground, and, okay.
He said E would be 0. Cause that's the same thing as, net force.
Total force?
Yeah, it'd be 0, cause velocity is constant.
Yep, so that answers the third one. The normal force, once you accept that they're all in equilibrium and therefore the total force has to be 0, looking at this right here, well, if the total force is 0, that means that the normal force acting on him from the sled has to be equal to his weight.
So 30, his mass? No, cause weight isn't mass, I'm sorry, my bad. Okay, so it'd be, the 35 kilograms times 9.8.
Yes, I believe it takes place on Earth. All right. So you multiply those together, you get his weight, you get the normal force therefore acting up on him, which has to be equal to the normal force he pushes down on the sled. The normal force acting on the sled from the ground, well, I've got one force acting up, that's the normal force from this normal force here from the ground, and I have these two forces acting down. Again, equilibrium, this force up must be equal to those forces down. So the weight of the sled, 10 kilograms
6.
mass?
6.
6, all right, so I have 6 times 9.8, which is something.
58.8.
And that would be sled from the ground?
That's the weight of the sled.
Oh, that's the weight of the sled.
The normal force acting on the sled from the boy, well, that's equal to his weight in this case. So 35 times 9.8, 343. So I have this 343 acting down on the sled from the boy. I have 58.8 acting down on the sled because the gravitational pull down on it, and the normal force, which is keeping it all in balance. So the normal force that the ground exerts on the sled would just be the sum of those.
Of each, oh, wow. I was
Okay.
thinking that, but I didn't think, that's why I was putting all types of different stuff in.
Okay.
What about the friction force?
What, acting on the boy?
No, oh, yeah, it says friction force acting on the boy from the sled.
All right,
0?
it's 0.
0?
Because he's moving horizontally along with the sled. In the wording, I say that his velocity is the same as the sled, or his velocity matches the sled. The
Yeah.
velocity of the sled is constant, therefore the force
Oh, okay.
acting on him has to be 0. Now, you've got the weight and the normal force acting on him, but there's also this horizontal force. If there's friction, it would be horizontal. If the friction is not 0, and he's in equilibrium, there's gotta be some other force acting on him.
And then the gravitational force?
Well, the gravitational force is down. If friction force is acting on him, there's gotta be something opposing the friction. And there's nothing else, so friction is 0.
Okay.
Unlike the sled does have friction acting on it, but that's because you've got this other force. All right. The I've almost lost at least one, so I think it might be time. If you need a little bit extra time to sort of study, feel free to do that, otherwise I'm gonna hand out the tests. And oh, that's not part of the test. And fortunately, the last page is blank, so I can just put it down, face down. You're still studying. Nope, that is the best.
I'm trying to get rid of it. You want just first and last name, or do you want the date?
No, it just,
Last name?
just something so I can identify it as yours.
Okay.
Yes. Yeah, so 2 calculators here, 3 calculators, 4 calculators. So 1, 2, 3. I'm seeing 3 calculators. Next calculator I find, I'm gonna go to Abby, and then if I can find the 5th one.
I don't mind sharing, you're right next to me.
Okay.
Are we allowed to?
You just clear it before the class is over. And if you have a calculator on your phone, just make sure that,
Okay, I can do it. Put it here as soon as I.
scars from the past, I've been burned by that before, so please.
There's one right there on the desk.
Already.
Oh, okay, got one more.
Who is the least
I guess-
trustworthy?
Really? He was also
Abby's
the next
passing
person
it
to
over.
ask.
In the tutoring lab, they might have some.
Pardon?
In the tutoring lab, they might have some.
Oh, okay, let's see if we can do that. Yeah, don't forget the back size. I might figure out the spandex. Like I said, to pass on, it doesn't do the really fancy something or another.
Oh, man, well, if I fail, remember that.
We'll blame Mike.